Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical, Nobel Prize-winning physicist Richard Feynman once said. His words now seem eerily prophetic as more scientists explore this mind-bending idea. Imagine waking up one day to learn that everything you see, feel, and experience, from the device you're reading this onto the stars in the distant galaxies, might actually be calculations in an unimaginably complex quantum computer. Not a simulation created by advanced beings, but reality itself operating as a vast information processor. Think about your computer for a moment. At its core, it processes information through billions of tiny switches that can be either on or off, ones or zeros. These binary digits or bits are the foundation of all computing. Now zoom out to the universe. What if space, time, and matter aren't the fundamental building blocks we've always thought? What if information is? This concept suggests that the universe doesn't just contain information, it is information. The laws of physics are like lines of code, particles like data points, and everything we see represents the output of cosmic calculations. John Wheeler, a pioneering physicist, coined the phrase "it from bit" to express how physical objects might emerge from information. In this view, reality emerges from a process similar to computation at its deepest level. To understand why scientists compare the universe to a quantum computer specifically, we need to grasp what makes quantum computers different. Regular computers use bits that must be either 0 or 1. Quantum computers use qubits that can exist in multiple states at once thanks to a property called superposition. One qubit can represent many possibilities simultaneously. Quantum computers also use entanglement, where qubits become linked in ways that classical physics can't explain. Change one qubit and its entangled partner changes instantly, no matter the distance between them. These properties let quantum computers explore countless possibilities at once, making them potentially far more powerful than regular computers for certain tasks. Sound familiar? The quantum world of particles also shows these exact same properties. Particles exist in multiple states until measured. They demonstrate entanglement across space. This striking similarity is one reason scientists wonder if the universe itself functions like a quantum computer. The idea isn't just philosophical daydreaming. Several scientific observations point in this direction. Quantum field theory, our most accurate description of the subatomic world, treats particles as excitations in fields that extend throughout space, similar to how information exists in a computing system. The holographic principle suggests that all the information in a volume of space can be encoded on its boundary surface. This parallels how information is processed and stored in computers. Seth Lloyd, a quantum physicist at MIT, calculated that the universe could have performed about 10 to the power of 120 operations on 10 to the power of 90 bits of information since the Big Bang. That's a lot of computing power. Information theory increasingly explains physical phenomena. For example, entropy, a measure of disorder in physics, can also be understood as information loss. Black holes appear to store information on their event horizons proportional to their surface area. Even space-time itself might be emergent rather than fundamental. String theorists and quantum gravity researchers are finding that space and time might be built from deeper quantum entanglement relationships, like how a computer screen image emerges from underlying code. If this view is correct, it changes everything and nothing at once. On one hand, your daily life continues unchanged. Apples still fall and dropped, the sun still rises, and you still need to file your taxes. On the other hand, it transforms our understanding of reality. Matter becomes less stuff and more process. The universe isn't a collection of objects, but a network of information processing. This perspective helps explain why quantum mechanics seem so strange. If reality is computation at its core, then quantum weirdness isn't strange at all. It's just how information processing works at the most fundamental level. It also has practical implications. If we better understand how reality processes information, we might develop more powerful technologies that tap into these processes. Our own quantum computers might one day work more like the universe itself. Here's where things get really strange. If the universe is a quantum computer, could we build a quantum computer powerful enough to simulate the entire universe? The short answer is probably not. To perfectly simulate a quantum system requires a computer at least as complex as the system itself. To simulate the entire universe would require a computer larger than the universe, which is impossible if we're inside it. This limitation is called the recursive simulation problem. You can't fully simulate the system you're inside without creating a paradox. But we don't need perfect simulations. We can create approximate models that capture the most important features of reality. This is what our current physics theories do. They're simplified models that work remarkably well despite leaving out details. The limits of simulation point to something deeper. There may be fundamental limits to knowledge that stem from our position as computing processes within the larger computation of the universe. Not all implications of the quantum computer universe are uplifting. This view raises uncomfortable questions about free will, consciousness, and purpose. If everything is computation following rules, are our choices predetermined by these rules? Is consciousness just a particular type of information processing? Does purpose exist in a universe of calculation? These questions aren't new. Philosophers have debated them for centuries. But viewing the universe as a quantum computer adds new dimensions to these old puzzles. The idea also contains inherent limitations. If we are computational processes within the larger computation, our understanding may always be limited by the same constraints that limit a subroutine from fully understanding the whole program it's part of. Some physicists argue that the quantum computer model of the universe isn't meant to be taken literally. It's just a useful metaphor that helps us make sense of bewildering quantum phenomena. Others see it as potentially the deepest truth we can access. If information is fundamental and reality is computation, this might be as close to the bottom turtle as we'll ever get in our understanding of existence. The truth likely lies somewhere in between. Models are maps, not territories. The universe as quantum computer perspective gives us powerful tools to navigate reality, but like all models, it will eventually be refined or replaced by even better descriptions. What's certain is that this perspective represents one of the most profound shifts in how we understand reality since Einstein's revelations about space and time. It suggests that beneath the physical world we perceive lies a deeper reality of information, relationship, and process. This view connects ancient philosophical questions with cutting-edge physics. It links the most abstract mathematics with the nature of consciousness itself. And it reminds us that reality may be stranger and more fascinating than we could have imagined. The next time you look up at the stars, consider that you might not just be observing distant suns, but witnessing the visible output of an unfathomably complex cosmic computation, one that includes you as both observer and calculation.